So we're going to just title this Bohr to Schrodinger. All right, now I'm not sure, we might get a little bit beyond Schrodinger, but we'll see how we do. So Niels Bohr's model, and we talked about his model, which was about electrons changing their energy levels in atoms, right? And when they fall back down, they give off light. They absorb energy, they go up. They fall back down, they give off light. Different elements give off different colors of light, apparently because their energy level structures are different. Just like if you had a bookshelf with, if we just took those shelves and moved them to different levels, we'd get different colors of light. The problem was his model worked great for the element hydrogen only. So it worked great for hydrogen. It failed for helium and above. So they realized, even though he had this great model that it worked great for predicting the wavelengths given off by hydrogen, it didn't work for larger atoms, so there were major issues. Okay? And there were other questions too. Even at Bohr's time, there were people saying, well, wait a minute here. What are the electrons doing around the atom at these energy levels? See, people were thinking about it around this time as planets going around the sun. Here's the problem. If electrons are rotating around the atom, then they're moving. Do you remember what happens when you have a charged particle that's moving? Like up and down? What happens? It makes light or radiation, at the very least, like radio waves or something. What that means is that every single atom everywhere would be constantly radiating electromagnetic radiation, which they're not. So something's going on there. And if they did, that would be a problem, because that would mean they would be constantly losing energy. So these atoms would all very quickly, in a matter of picoseconds, spiral into the nucleus. All the electrons would collapse into the nucleus. So the lifetime of an atom would be very short. So there were major problems with this whole picture. What was going on? There's a guy named Lewis who was kind of picturing electrons in shells around atoms just kind of repelling each other. He had them like points on the edge of a cube. So there was different ideas. But along comes a guy who was trying to answer this question. So we have this one question in particular. Why can electrons exist only at certain energy levels? Now, there were lots of questions about the current model of the atom, but I'm just going to focus in on this one. Why can electrons exist only at certain energy levels? Because that was what it seemed was the case. Bohr's model seemed to be saying electrons can only exist at certain energy levels. Even though it failed for helium, it was kind of easy to understand why it might fail for the larger elements. They're much more complicated. You've got more electrons, and those electrons are going to affect the energy levels, and they're going to be kind of interacting with each other constantly. So it makes it a much more complicated problem. So it did seem like Bohr had it right, that electrons can exist only at certain energy levels. But why? Along comes a guy in 19... I just had this. '24. The guy's name was Louis de Broglie. And here's what he did. He just said this: what if... Now, think about this. If you remember way back at the beginning of the year, I had this little video that you were supposed to watch that was about a guy named Karl Popper. And this guy, Karl Popper, had this philosophy of science that he said science was all about conjectures and refutations. So you start by just making a conjecture, which can essentially be a wild guess. We don't usually think about it like that, but it can be. And then you test it. So you make a conjecture, which is what he was doing. What if electrons were standing waves? So this is his kind of wild, imaginative guess, and I don't know what led him to think this. Maybe it was just thinking about how photons can be waves and particles, and he's saying, wait a minute, light can be waves and particles. What if all particles can be waves? And what would be the implications of that? Now, he kind of put this together. It's kind of cool how he did this. He actually looked at two equations that we've already seen. He looked at the Planck-Einstein equation for the energy of a photon, and he looked at, which of course this can also be written like this. Do you understand that? See what I did there? I just substituted the speed of light in there and the wavelength so that we can express it in terms of wavelength. C over lambda is equal to the frequency. I don't want to lose you. Do you see what I did there? So then he also looked at, and this is pretty cool, he used Einstein's equation. And he just looked at these and said, well, wait a minute, look at that. They're both equaling energy. What would happen if I set them equal to each other? That seems to say that there's some relationship between mass and wavelength, right? That there's this kind of mass-wavelength thing going on. And then he says, well, I'm working with electrons. They're not moving at the speed of light. So what if I do, instead of the speed of light, I'm just going to use v, which is just the velocity of the electron. Speed of the electron. However fast the electron happens to be moving. Electrons, by the way, can move at different speeds. So you could shoot an electron really fast. It could be moving different speeds, even an atom, theoretically. So the velocity of the electron, he's going to substitute that in now. So let's just go in here, and now I'm going to put in velocity wherever I had the speed of light. Now that's the speed of the electron. Now let's just solve for, we don't have to do this, but we'll solve for the wavelength now. Wavelength would be equal to hv over mv squared. One of those velocities would cancel, so I would have h over mv, where m is the mass of the electron, v is the velocity. V is the velocity of the electron. Now, how does this answer the problem? If electrons are not just waves around atoms, but standing waves, they're resonating. So think back to when we talked about standing waves. That's when you get this constructive interference, and the wave is kind of matching up. We looked at it like this. For a standing wave, we looked at something maybe like this, where here I am shaking this rope with a hand growing out of my head, okay? And this is, okay. So a standing wave shows this kind of pattern where the wave appears to be moving in only certain parts, and then we have something called nodes. Now, the interesting thing about standing waves, which, by the way, when you have a standing wave, you have resonance. Okay? Interesting thing about standing waves is that they can only occur with certain wavelengths in a given situation. So, like in this case here, this wall right here, where it's attached to the wall, must be a node. Okay? That must be a point where a crest is exactly aligned with a trough coming from the opposite direction. So, a crest coming from this direction is exactly aligned with a trough from the other all the time. All the time. That's why it's getting canceled out. Or at least the positive displacement is exactly equal to the negative displacement. I should say it like that all the time. And right here, we have constructive interference, where they're adding to each other. And they have to add up. So like in this case, I have, let's see, something like, this looks like 1 3/4 waves or something like that. Okay, see what I'm saying? If I look how many wavelengths fit in here, this would be 1 full wave. But you can't just take any fraction of the wavelength and say I'm going to have like 2 1/3 waves. It wouldn't work. It's going to have to be like 1/4, 1/2, or a whole. Otherwise, the standing wave pattern will not work. Because my hand has to be an antinode. It has to be the maximum displacement, and this has to be 0 displacement right here. Yeah, so a wave, 1 full wavelength would be from crest and then up to the next crest like that. That would be 1 full wavelength. And so here's the thing. If electrons around atoms are standing waves, then they can only have certain frequencies. Okay? Standing waves in a musical instrument can only have certain frequencies. Right? And if only certain frequencies, let's look back at Planck's equation. If only certain frequencies, then only certain energies are permitted. So if you think about atoms as little musical instruments, little tuning forks, who can only vibrate at certain frequencies, then that's what we're talking about here. Although they're not necessarily vibrating, we don't really know what they're doing, but they can only have certain frequencies. And then, so the idea is if you were to increase the energy of the electron, you'd be raising the frequency, right? You'd be changing the energy of the electron. So you'd be going up an energy level like that on the atom. Now that's kind of weird, so what I want to do is I want to show you a little demo of this. If you look on my old e-board here, and you click, if you go down to this one, standing waves in the circular membrane, this is going to show you a similar thing to that, just with a little applet. So let's, and this one can kind of, can you all see that? This is a drum. So this is you can view this as a drum. This is the lowest frequency standing wave that can occur in the drum. Say you just strike it in the center. Okay, that's what you're going to get. Now, if I go to a higher frequency, the next standing wave would look like this. Now, folks, this is exactly what we were seeing on that plate. The node, where's the node? The node is right about here. You see that? Where it's really not oscillating at all. And of course, the edge in this case is a node, which is different than the plate. The plate we had, the edge was not a node because it was free to fluctuate. In a drum, the edge is a node because it's forced into place. Why won't it shut off?
So funny.
All right, hang on. Fix this thing. Hang on. That was more than one wave all kind of interacting with each other. This is a standing wave at the third resonant frequency. And so you could see the same thing, concentric rings. Now, if you're wondering about how this applies to an atom, try to picture this in 3 dimensions in a sphere, because it could happen in a sphere. And that's what we're going to see in a minute as we look closer at the atom. But picture this wave happening in a sphere. And we can, of course, increase the frequencies here and stuff. And we could just keep going up in frequency. And then, just like on the, sorry, doesn't respond very quickly sometimes. There we go. Again, more and more concentric rings, just like the Chladni plate we just looked at. You can kind of get the feeling looking at this that this has more energy, right? That this would be more energetic at this, in this case here, than the lower frequencies. Now, somebody asked, what if we go across? Somebody in the other class said, well, what if we go across? That is, what if we start the oscillation somewhere else but the center? So, for example, to the side, okay? So let's say you struck the drum on the side, you get this sort of thing, where the center is a node. And you can go, now the reason I'm showing you this is because, did any of you watch the Khan Academy videos yet that I had up there? When you look at what electrons are doing in atoms, the lowest energy state of each energy level, what Bohr would say the n level, n equals 1, n equals 2. The lowest energy state electrons are all in spherical shaped areas, okay? But within some of the energy levels, they can be in other types of areas with other shapes. And in some cases, the electrons can actually be in kind of a dumbbell-shaped area around the atom. So they're kind of like a figure 8 sort of thing. In fact, we can even, that's not what I'm looking for. We can do something like this. In which case, we've actually got them going along 2 axes, right? That would be if you hit like here and then at 90 degrees to that, something like that. Okay, now, if you want to see why Bohr's model fails, let's highlight more than one at the same time and see what happens. So let's say you've got 2 electrons in there at the same time. Even with just this situation here, things get much more complicated, right? So it gets much harder to analyze this. As we continue to add more, that's just with 2 electrons. Now we got 3. Throw some of these others in here.
That's so cool.
And you've got some pretty freaky stuff going on. So here is a relatively simple atom here, still with kind of a crazy wave pattern going on. All right. So we've got interactions between the waves that we need to worry about. All right. I don't know if my system can handle this. It looks like it's freezing up on me. All right. So let's talk a little bit more before we look at that again. We'll come back to that or something like it. So that's basically what you guys saw with the Chladni plates. And my computer's freezing up on me. Okay. So, de Broglie's got this weird idea, but it seems to make sense, right? The next step was 1926 with Erwin Schrödinger. What's that? I'm sorry. What? Well, that electrons were standing waves. What I should say is, I guess he said, what if electrons were standing waves? Well, the answer is, this can explain why electrons can only have certain energy levels. Can only exist at certain energy levels. So that was a piece of the puzzle. I mean, you can kind of look at this as puzzle pieces coming into view. And they're able to kind of put them together and think, and this gives us a hint about what might be going on a little bit further. Then we have this guy named Schrödinger. He says, all right, if electrons are waves, let's apply the full weight of wave mechanics to the electron. So this guy's a physicist, he knows all about waves, and he writes this equation. Now I'm just going to show this to you. Obviously we're not going to do calculations with this. This is the equation for the electron wave, written by Irvin. What's that? What's that? It is it's called psi. It's a Greek letter. It's uppercase P-S-I, psi. And this is over this.
Is that an X on the bottom? Or
That is an X, yes. Now, why is there an X there? This is for one dimension. Now, so folks, this looks complicated, but this is for an electron moving in one dimension only. So this is not the actual equation for an electron in an atom, which would have X, Y, and Z all in this. This, any of you who have dabbled in calculus notice that this is a differential equation. And so the lowercase d is means a very small change, okay? And in this case, it's a second derivative, so it's the change in the change, right? So this is the first derivative is the change in the slope with x, and the second derivative is the change in the slope, right? The rate at which the slope is changing. So this is not simple, and that's why I'm not. But I throw this up here because there's some interesting things about it. One is, what's pi doing in here? Well, this is a wave, right? And so you can use pi shows up in wave equations. Planck's constant. I guess we're not too surprised to see Planck's constant in there, right? Since we're talking about something at the quantum level. This is energy. We're not too worried. We're not too surprised to see energy there. This is actually the potential energy. One of these is kinetic, one is potential. So it's the difference between potential and kinetic energy. So these are energy terms. And this is just the mass. Now this thing, actually, if this was in 3 dimensions, it would fully describe the electron in the atom. And it works. It works. You can do calculations. We'll see some of the consequences of this, even though we won't actually be doing any calculations with it. Okay? So this is in 1 dimension only. Now, the weird thing about this equation is this guy. This is the strangest thing about it. It's got a prominent place in the equation. And of course, it's called psi. That's just the word for that symbol. But it is called the wave function. Quantum mechanics is really weird. And one of the things that this shows you is if you have any interest at all in quantum physics, you need to take math to as high a level as you can. That's the essential idea. To deal with this kind of stuff, you have to have high levels of mathematics. This is a wave function, and it is, I guess, the way that he would have interpreted it is, at that time, it's the amplitude of the electron wave. Do you remember what amplitude is? It's the height of the oscillation, right? So psi is the amplitude of the electron wave. Here's the problem. What does that mean? And at the time when Schrödinger wrote this, no one knew. In fact, it's debatable even now, and there are different interpretations of what that means. What does that mean? I can see when I look at that plate vibrating with the sand on it, I can understand what amplitude means. It means how far up is the plate moving. That's amplitude. Okay? I can see that a wave out in the ocean has a certain amplitude, depending, it's the height of the wave. What is the amplitude of an electron wave? Okay, now this gets to the heart of the matter because it's really like, it reveals the fact that we don't really understand what it means for an electron to be a wave. Okay? It is not just a wave in the electromagnetic field. That's one thing that we know. It's something in and of itself. In fact, sometimes it behaves like a particle, sometimes it behaves like a wave. So what does it mean? The first hint came from a guy named Max Born. And I don't know exactly when, I don't have a date for this one, but by the way, yes, there are several B names in here. We've got Bohr, de Broglie, Born, and we might throw one more in there for fun later, another B name, Bohm, B-O-H-M. If I can think, maybe I'll throw Boyle in there as just a trick on the answer. Multiple choice. But this guy Born, he interpreted psi. And here's what he said. He said, I don't know what psi, this isn't a direct quote, okay? I don't know what psi means. He said, I don't know what psi means, but, and here is the key, psi squared, if you square it, it is proportional to the probability of finding an electron at location X in the Schrödinger equation. So if you solve the Schrödinger equation you put X in there and you solve it for psi and you square psi, that actually gives you a number that is proportional to the probability of finding the electron at X. Now what does that mean? That means at the nodes, probability is 0. Okay, so let's take this a little bit further. We'll say at the nodes, the probability is 0. At the nodes, the probability is 0. At the antinodes, it is maximized. So now this makes a little more sense, because and actually that little thing with the sand is kind of a good illustration here, although it's totally in reverse. All right. In the case of electrons, if you think about the sand particles on that plate as being electrons, it's totally reversed, because the sand was more likely to collect at the nodes. In the case of an electron, we would expect to find them at the antinodes around the atom. So in these kind of concentric rings around the atom. Now basically, if we go back to the e-board here, I've got another applet I want to show you, if I can open this thing. Actually, let me do it like this instead. Let me do it like this first, then I'll show you this applet. I'm going to draw a graph of psi squared. Now, here's one of the things that we just brought out that I think I mentioned this briefly when we were talking about radioactive decay. This kind of randomness that is inherent to things at the quantum scale. All right? We've seen this before, but darn it. If I had, I'm going to call this an atom in a box. If I had an atom in a box and it only had one electron, so this is, say, a hydrogen atom, it's in a box, and there's the proton in the nucleus, and what I'm going to do is I'm going to open the box, and I'm going to see where the electron is, all right? There it is. I close the box. I open it again. There it is. I close the box. One of the weirdest things about quantum mechanics is that you can't predict where it will be next. It's impossible. You can predict with a certain probability where it will be next. It's more likely to be closer to the nucleus if it's in its first energy level. Right? If it's in energy level 1, n equals 1. In other words, if this electron has not been excited by anything, it's in what we call the ground state, it's resting. The atom is at rest. We haven't zapped it with a high voltage electrical field, we haven't put it in a flame, we haven't shined X-rays on it or UV light. All right? It's in its ground state. Here's what would happen if I'm going to keep opening it and I'm going to keep plotting where I see it. So every time I see the electron, I'm going to put a dot on the little drawing here. This is what it looks like. Appears to be not totally random, but I can predict probabilities of finding it, but I can't tell for sure where it's going to be next. In fact, it's, like I said, it's impossible. Theoretically impossible to predict that. This is why we're talking about probability functions. So let's make a graph. Okay, make a graph here. This is going to be x. This is distance from the nucleus. Actually, let's make this r, sorry. Radius, so this is distance from the nucleus. And on this, we're going to put psi squared. Now remember what psi squared is. It's the probability of finding an electron, or it's proportional to the probability of finding an electron. Here's what we would find. Something like this. Drops off like that. That's in the ground state. This is what we would call n equals 1. This would be that low energy level. Okay. Now, what's that? R, yeah, R for radius. But it's the radius out from the nucleus. So as we increase the radius. Now, this is what we would find if we did this kind of detection. Let's say I had a little box on the end of a stick. And I'm going to stick this box in the, so I'm sticking this box inside of the atom box, and I'm moving it around, and whenever an electron hits it, it goes tick, and then I mark it down on my graph. This is what I would find. So it's a tiny little box on the end of a stick, and whenever it catches an electron in there, it clicks. That's what I would find. Now, if I looked at it a little bit differently, I'd get a little different graph. And right now, the reason I want to do this is because right now this might, if you're thinking about it, it might be confusing you because you're thinking that doesn't look like a ring. That doesn't look like a ring of electrons, that graph. It looks like just a cluster of electrons around the nucleus. Do you see what I'm saying? They're just clustered around the nucleus. They're not in a ring. But if I do a different kind of detection, if I detect the surface of a sphere and I move this sphere out, so let's say instead of a little box detector, I have a balloon on a stick. And I put this balloon around the nucleus, and then I inflate the balloon, and as the balloon's going out, whenever an electron hits the surface of the balloon, it goes tick. What am I doing now? Now I'm detecting the radius at which I might find an electron. It's a little bit different. I would then see something. So this one right here gives me this. And if I do a little bit different kind of detection, I see this. So with a balloon, with a three-dimensional detector that's increasing its radius so that I'm detecting the entire surface of the sphere as I go out, this is what I would find. Now that looks more like a ring. Because picture this graph rotated around in 3 dimensions. And what you would have is a ring, or what we more commonly call a shell. Have you ever heard that term? In terms with electrons and atoms, a shell? Picture this as being a shell of electron, of probability around this atom. That's where the electron's most likely to be, is in this zone right here. And this right here is the most probable radius. And it turns out, and this is kind of cool, that if you do this calculation for hydrogen with the Schrödinger equation, it matches Niels Bohr's